Let us introduce the subject of composite reshaping. After being sorted by the NDT measurements and decision support system in Week 2, Module 1, some parts are directed towards a repairing process, others towards a fiber matrix separation, and others towards a reshaping process. The goal of the reshaping is to modify the geometry of a composite part to use it for another goal, with inducing permanent deformation while minimizing the loss of properties. A good example could be changing the geometry of a curved board hull to make a flat board for a table. The reshaping process is achieved through one of two methods, a batch process and a semi-continuous process. The first involves feeding the composite between two counterparts of a hot press. The second relies on a rolling machine with two hot counter-rotating cylinders. Obviously, this will require some material characterizations, Week 3, Module 4, which involves a set of mechanical tests realized under the effect of temperature. The tests to be carried out simulate the phenomena that occur during the reshaping process. This includes traction, bending, stress relaxation, creep recovery, friction, etc. The studied specimens are made of pure polyester resin and as well as composites with different configurations. Unidirectional tensile tests are important to investigate a material's tensile deformation and stress at rupture. They can be carried out at different loading speeds and different temperatures. From previous works, it can be noted that the greatest interest is directed towards the material's behavior at 98 degrees Celsius. At this temperature, the resin manifests a significant softness and an increased level of deformation at rupture. While changing the geometry, bending is an important aspect of the reshaping process. That is why we study the flexural behavior of the composite. Due to its high heterogeneity, 4-point bending tests are carried out. They permit us to avoid early stress concentration, as in the case of 3-point bending. They also enable us to locate the limits of bending stress and deformation of our material. Different compositions are tested and compared. Another important aspect of reshaping comes from introducing permanent deformation into the composite. Knowing that the resin is the component that controls this aspect, relaxation and creep recovery tests are one approach to evaluate it. This requires subjecting the material to long cycles of sustained deformation and zero stress, respectively. Modifying the operating conditions, such as time, deformation, enables us to locate the optimal range where we can obtain the highest final deformation. Rectangular resin specimens are tested in tensile mode, as it is the one that provides the most accessible information in terms of deformation and stress within the specimen. The goal set for reshaping is to ensure the flatness of the reformed part along its life cycle. The final product of this process has to guard its new geometry so that it would be reusable in another applications. So, next would be to evaluate if the material is capable of recovering its initial shape. This requires studying the evolution of the reshaped specimen's geometry with time. After being reformed, composite and resin specimens will be heated at different temperatures for certain periods of time. After each heating cycle, the specimen's shape is traced and the percentage of recovery can be measured. This permits us to know the effect of temperature and time on the life cycle of the final product. The time temperature equivalence is a principle we can rely on to simulate the recovery over long periods of time through shifting the data points of multiple curves to obtain one master curve for each temperature. After achieving the goal of reshaping, the last step would be to perform non-destructive testing, or NDT for short.